Hello world, this is Craig. So continuing looking at this little iSBC that I just received in the mail, I'm going to bring it up today. So the first thing I do before I bring one of these boards up is just do a really good inspection. Make sure that all the capacitors are still attached, and the wire wrap pins or the shorting pins will invariably be bent over. So I use my little wire wrapping tool to simply straighten these guys out. Make sure that they're not shorted. Get them all nice and back and vertical. So I do that for the whole board. You know, you can look at all the scratches on the tops of these chips and the tops of some of the capacitors. That this spent a long time sliding around on something, and so quite likely on the back also it slid around. And so when that happens, the pins from the sockets and the chips wind up getting bent over. And so I want to make sure that none of those are touched. So I use my best side cutters and eye protection on this because these guys fly, and cut off anybody that looks like he's long enough to touch someone else. And part of this is because when I store these, I store them in the file folders, and I just want to make sure that sometime in the future I don't bend one of these over and short somebody out that could cause damage. Certainly cause the board not to work, but possibly cause damage also. Okay, so normally I'll have this up on its edge so the pieces don't fall back onto the board, and I'm going to go and trim off the back of all of these. Okay, so I have straightened all my pins using my wire wrap tool, and on the back I have cut off all of the leads or all the backs of the pins, and this board had really gotten a little bit of it took some hits on the back because even some of the machined pins on this were bent over, and there actually were a couple that I'm not sure if they were touching, but they were very close. And that couple things I want to re-emphasize. One is use an appropriate pair of side cutters, because you want to make sure that you're not applying stress to any of these when you're cutting them off. And these little Excellite side cutters, these little nippers, are just perfect for this. In fact, I think that's what they're made for. The second thing is to make sure you use eye protection, because these things, they just shoot off this when you cut them. So make sure you use eye protection. Cover your coffee to make sure that you don't wind up with some little tips in the bottom of your coffee. Now I'm going to depopulate the EPROMs, and I can use a screwdriver for this, of course, but I prefer to use these little chip grabbers. That guy's give me a battle. Everything's straight, and the next thing we're going to do is put this in the card cage and bring the power up on it. Unless you know for sure right now you're not going to enjoy this hobby, you need to get yourself some kind of a card cage. What I'm going to do is power it up slowly over a fairly long period of time. I'm not sure if this actually works, if you can reform some of these capacitors, but nonetheless, you know, I've had enough boards that you power them, you put them in, you pop on the 5 volt and the 12 volts and the -5, and sure enough, you know, you'll pop the capacitor. I will, the first time I get a board, I'll bring it up, the 5 volt power supply up to a volt, and the 12 volt power supply is up to a couple of volts. And as I bring them up, I'll watch the current, and I'll increase them every hour or so, all the way up to their final voltage. So this will take the good part of a day. I'll go off and do something else while I'm raising this. But the idea is that we're trying to reform some of the oxide, some of the insulating in the capacitors, and we do that by bringing them up slowly. So whether it actually works or not, I can't vouch for, but I do have better luck with boards, I think, if I do bring them up. The nice thing about these is, of course, they have their voltage, but they've also show the current draw without having to flip back and forth a bunch, because we are watching the current draw in this. This is what's telling us about the health of the board. So I have these set up for my 5s, my plus and minus 12, my -5. This board doesn't use 10, so I've just got my 10. My 10 is still on. over time, I'll just bring the voltage up on all of these together. Okay, so we're at the first setting, so let's let this thing set for a while, and while it does that, read through the instructions, because the next thing we're going to do is jumpers. Okay, the board is all powered up. All the capacitors seem to have held okay. The voltages came up okay, so nothing is being lugged down. If we look in the user's manual, here's table 1. Table 1 shows us what the currents should be without the EEPROM, without any EEPROMs at all. And on the 5 volts we should have 2 amps, and in real life we have 1.4 amps. The 12 volts, 150 milliamps, and we are running about 6 milliamps. And the minus 5 volts, 2 milliamps, and we're seeing it's not being measured, and it's being measured, but it's too low for the thing to pick it up. And the minus 12 up to 175 milliamps, and we have 2 milliamps on that. So the currents are all well within specs, and so we're very happy about that. Now let's go down and look at the jumper table. So that's this table 2.8, the 84, 85, 86 set. So here's 84, 85, and you can see the asterisk means that that's by default. 84, 85 connects the BPRN to the board. This is the bus priority M to that board. 85, 86 implements BPRN multibus compatible. Basically, 84, 85 means ignore the bus or treat the bus differently for the master priority in, and 85, 86 make sure that it's multibus compatible. The other one I want to look at is the 82, 83 jumper. By default, 82, 83 is installed, and that connects the reset to the multibus. Sheet 2 of the schematic. For right now, we just want to bring this thing up. We want to see if anything works at all. We're going to look at these jumpers. Here's our 84, 85, 86 set that is for the bus priority in. What we're going to do on this is we're just going to take this jumper out, because depending if we have the jumper on 84, 85, 86, it either lets this board control that, or it follows the multibus standard here on P1 finger 15. But in either case, we don't care about any of that. We simply want to make sure that this hold is low. So what this bus priority in does is, if any other bus master needs to have the bus, it will activate the bus priority in, and what that will do is make all lower priority processors go into a hold state. And so this hold line will go high, and this processor would go into hold. And of course, we're trying to bring this processor up, so if it's in hold, it's not going to be doing anything. To eliminate this part of the circuit and also eliminate anything that might be out here in the bus priority in, we're simply going to take the 84, 85 jumper off. Now normally a TTL input that is not taken one way or the other will generally drift high, but these have a pull down on it. If we take this 84, 85 jumper off, hold will be pulled down to deactivate, so it will be disabled. That will guarantee that no matter what's going on with the bus out here or with any of the rest of the circuitry, we're not going to be in a hold state. First thing we're going to do is take the 84, 85 jumper off, and it's good that we checked this because they had this set to 85, 86. This would have required the external bus priority input to be at 0 so that this would have been enabled. The way it was jumpered, this bus or this board would not have come up. So we take 84, 85 off is the upshot. The other thing I'm going to look at is this 82, 83. We want to make sure that 82, 83 is in place, because the purpose of the 82, 83 jumper is to allow the 8224 clock chip to generate the reset for the processor. Again, interesting, in this board as received, 8283 was not in place, and what that means is that the reset would have had to come from the bus. They had either the back plane or another card in this system that was providing the reset signal. They had this essentially disabled. So the reset had to come in through this P114 to do the reset for the board. So we put the 8283 jumper back in so that this clock then will generate the reset. So what's going to happen is we power up. There's an RC circuit right here that is slowly going to bring the voltage up. While we're here, let's look at the internals of the 8224. So here's the reset in. First thing it does is it goes through a Schmitt trigger. And we'll look at, when we see in the waveforms, the function of this and the beauty of the Schmitt trigger. As soon as there's enough voltage on this chip, the clock will fire up. As soon as the clock fires up, it'll wait for this reset in to grow. As soon as it gets to a certain value, the Schmitt trigger will flip that to a logic 1. That will get clocked in and clocked out onto the reset, and that'll reset the board. Okay, here's the waveforms of a power-up. And let's get oriented first. Channel 8, the very first channel, is Phi 1 coming out of the 8224 clock chip. Channel 7 is Phi 2. And 15 is the TTL clock. So that's the TTL representation of the Phi 2. So those are the 3 digital measurements on the clock chip. The next 2 blue ones are the analog measurements of Phi 1 and Phi 2. We move down. Channel 10 is the actual RC circuit itself. So that's the circuit that charges slowly to give everything time to be configured and get a good hard reboot once the power supplies are at high enough voltages. Channel 9 is the reset in to the 8080. So this is the digital representation and the analog measurement for that. And then finally the bottom one is channel 11. That's the sync signal coming back out of the 8080. So first the 12 volt comes on, and when that happens, the 2 clock outputs go to the 12 volts, and it's a good time to remember that be careful with your logic analyzer. It may not be able to handle the 12 volt inputs from the clock chip. And this board has -5 volts, plus 12 volts, and -12 volts. So a lot of logic analyzers can only handle the 5 volts. So before you start probing around too much, make sure that your logic analyzer can handle the negative voltages and the 12 volts. Otherwise, you might have to protect the logic analyzer. Okay, so the 12 volts comes up. Short time later, the 5 volt comes up, and you can see that the 8080 gets a few resets while the 5 volt is coming up. But until there's 5 volts, the clock does nothing. It just sits at 12 volts. As the 5 volt comes up, you can see both of the Phi 1 and Phi 2 begin clocking out. So let's look at the RC circuit here. The circuit is coming on up. It starts at 0 and it's coming up to eventually 5 volts. And as that comes up, there's a period here where the actual, it's right at the threshold. So the digital value of that, unknown. It's not stable. And so if the processor were allowed to simply follow that and go through the reset cycle, it would constantly be resetting and starting the code and then resetting, starting the code, resetting, starting the code. So we want to avoid that. So looking at 10, which is the RC analog value, and this above it is the RC digital representation of that. Below that is the actual reset in after it's gone through the clock, where first thing that happens, it goes through a Schottky, and then it actually goes through it gets phased with the clock. It gets synchronized with the clock. So we can see that the voltage comes up, and then suddenly, as soon as the Schmitt trigger is at the proper value, the reset drops down, the 8080 comes out of reset. There is one little glitch here where it is given a second reset. So in this case, it would have started code, and then it immediately, within a couple of t-states here, it immediately would be reset and started code again, and then that's the final one. But once it gets that second reset done, then it's good to go. These are all beautiful, and to make it even better, if we look at channel 11, that's the sync signal. So that's the signal coming out of the 8080, indicating that it is about to do a fetch of a instruction, or it's just about to do a machine cycle. And so every time before the machine cycle, it does the sync pulse. And so we're seeing these sync pulses come out. So that tells us that the 8080 is in fact expecting that it is reading in instructions off of the bus. This is fantastic. This means that the processor came up, the resets look great. We will zoom in here and look at the clock. Let's go ahead and do that and make sure that the clocks are looking okay, but from an overall perspective, this is a beautiful startup. Here's another sample and zooming in and looking at the clock pulses. So again, the top three traces are phi 1, phi 2, and the TTL clock. And then the next in blue are phi 1 and phi 2 again, but they're analog representation. And this is the highest acquisition rate for the logic analyzer, so this is the best that we can get with it in terms of resolution. You can also look at these on the oscilloscope and confirm that they are in fact proper sequence and proper level, and that they do have sharp corners. But let's look at the clock. So the clock coming out, the phi 1 and phi 2 clock coming out, is what's called a 252 signal. So that means that the first two is phi 1. Phi 1 lasts for 2 ticks of the crystal. So you can see here I have the annotations up and the timing pair. This is 0.11 microseconds. So that's 2 ticks of the 18 megahertz crystal. The phi 2 is the 5 of the 252. So the phi 2 is high for 5 ticks of that crystal, and then there's 2 ticks where both are low. So again, it's a 252, meaning that phi 1 is high for 2 ticks, and then it goes low. Phi 2 goes high for 5 ticks, and then it goes low, and then both remain low for 2 more ticks, and then the process repeats. So we can see that this is doing that. And it's hard to tell the timing exactly because the resolution is not that great. But on the oscilloscope, we can see that it is in fact doing that. And our voltage levels are within the specs required. A output low should be less than 0.45 volts, and an output high should be greater than 9.4 volts. And we can see that just generally it is hitting those. The waveform is showing that the high is about 11 volts and the low is very close to 0, maybe a bit negative. We can pick a value here. This shows the high as being 10.4 volts. The low is negative half a volt. On this one, the low is minus 0.78 volts, and the highest that we're seeing is 10.92. So they're hitting the rails as they should. Just as with the original power-up, this all looks great on this processor, so I think we are good to go. Now, if we don't get a good reset on this processor, what we saw in ours was a beautiful voltage rise and a clearing trigger on the reset in. But if we don't get it, the first thing we're going to start doing is looking at this C7. I've had C7 fail before. Check C7 if necessary. Might need to take it out, make sure it's not shorted, because of course if C7 is shorted, then the reset in is always held at ground, and the clock will not give a good reset out, and the processor won't start. It'll just be continually stuck in reset. So if you don't get a good waveform on the reset, or the RC circuit going into the reset in the 8224, first thing you want to do is check that C7 capacitor in that RC. And if you're not getting good clock outputs that are hitting the voltage requirements of logic 0, which is less than half a volt, or logic 1, which is about 9.5 volts, and you're not getting a good TTL output of the clock, of course, then the 8224 is likely bad. But we're fortunate on this board that all of that looks good, so we're going to move on. Thanks for watching. We'll continue this in a later video.